Welcome to The Explainer. Today we're going to talk about something that literally powers our entire world, but, most of us just take it for granted. I'm talking about electricity. So let's dive right in. Seriously, have you ever just stopped and thought about it? You flip a switch and boom, light. It feels instantaneous, almost like magic, right? But behind that one simple click, there's this incredible world of physics at play. And today, we're going to pull back the curtain and see exactly how that little spark lights up an entire room. Okay, so where do we even begin with all this? Well, let's start with the most basic idea. For anything to happen, for a light to turn on, for your phone to charge, something's got to be moving. And in the world of electricity, that something is what we call electric charge. So what we call electric current is, at its heart, just that, charge in motion. It's that simple. Imagine a copper wire. That current we talk about, it's really just a massive, coordinated stampede of electrons. Billions and billions of them, all flowing together in the same direction. The best way to get your head around this is to think about a river. Seriously, water flowing in a river, that's a water current. Well, electrons flowing in a wire, that's an electric current. The wire is just the riverbed, guiding all those electrons along. And of course, we need a way to measure this flow, right? We do that with a unit called the ampere, or what you've probably heard of as amps. So next time you see a charger that says it provides 1 amp, all that means is it's pushing a specific amount of charge through that cable every single second. But here's the thing. This flow of electrons, it's not just some random, chaotic mess. No, it's actually governed by this surprisingly simple but incredibly powerful rule. A rule that connects everything we're about to talk about. Okay, let's go back to our river analogy for a sec. What makes the water flow in the first place? It's pressure, right? A difference in height or something pushing it. Well, in electricity, that push has a name, voltage. And what about things that slow the water down? Like a narrow part of the river or a bunch of rocks? That's friction, and in our world, we call that resistance. The key is you always need that push, the voltage, to overcome the friction, the resistance. And this brings us to the big one, the golden rule. Back in the 1820s, a guy named George Simon Ohm figured out this exact relationship. He realized that the voltage, that's our push, is directly proportional to the current, which is the flow. It's so elegant. You double the push, you get double the flow. Simple as that, as long as, the wire doesn't heat up or anything. And he boiled it all down to one of the most famous and fundamental equations in all of physics. Voltage equals current times resistance. V equals I times R. That's it. That's Ohm's law. And I'm not kidding. This little formula is the key to understanding basically everything, from how your phone charges to how the entire power grid works. And look, you can see it right here in the data from a real experiment. As you crank up the voltage, the push, what happens? The current, the flow, goes up right alongside it. But here's the really cool part. If you divide the voltage by the current for each of these measurements, you get pretty much the same number every time. That constant value, that is the resistance of the wire. And we measure it in, you guessed it, ohms. And this law is just so practical. Let's say you've got a component. You don't know what it is, but you've hooked it up to a 12-volt battery, and you measure a tiny little current of 2.5 milliamps flowing through it. With Ohm's law, you can just plug in the numbers and bam, its resistance is exactly 4,800 ohms. It's like a little puzzle solver. All right, so now we get it. We have our 3 key players, voltage, current, and resistance. We know the rules of the game, Ohm's law. So now we can start building stuff. And when you're designing a circuit, there are really only 2 fundamental ways you can connect your components. First up is series. Think of it like a conga line. You connect everything end to end, one after the other. The current has only one path to follow, so it's the same for every single component. But the resistance adds up. The other way is parallel. Here, you give the current choices, multiple branches it can flow down. In this case, the voltage is the same for each branch. But the weird thing is, the total resistance actually decreases. This is the classic example. Those old-school holiday lights, one bulb goes out, the whole string dies. That's a series circuit. Your house, you can unplug your toaster and the lights stay on. That's because it's all wired in parallel. Okay, so let's put this theory into practice with a fun little challenge. This is a classic one. Imagine I give you 3 identical building blocks. They're all 6-ohm resistors. Your mission, should you choose to accept it, is to figure out how to connect them to get a total resistance of exactly 9 ohms. How would you do it? All right, you ready for the solution? It's a 2-step process. First, you take 2 of those 6-ohm resistors and you connect them in parallel. Now that combination gives you a new combined resistance of just 3 ohms.
Then you take that 3 ohm unit you just made and you connect it in series, in a line, with your last 6 ohm resistor. So what's the total? 3 ohms plus 6 ohms equals 9 ohms. Boom, mission accomplished.
So, this is all great. We can control the flow, we can design circuits, but so what? What does this flow of electrons actually do in the real world? Well, it turns out when you force a current through something with resistance, things start to happen. Specifically, things start to get hot.
This whole phenomenon is described by something called Joule's law of heating. And here is the absolute most important part to remember. The heat that's generated isn't just proportional to the current. It's proportional to the current squared. Let that sink in. That means if you double the current flowing through a wire, you don't get double the heat. You get 4 times the heat. This can be a really good thing, like in your toaster, or a really, really bad thing, like in your laptop when it's about to melt.
And guess what? This is exactly how an old-fashioned incandescent light bulb works. It's all about choosing the right material for the job. We use tungsten for the filament for a few very specific reasons. It has a crazy high melting point and a pretty high resistance, so we can just jam a bunch of current through it. It gets super, super hot. So hot that it glows white hot, and it doesn't just melt into a puddle. We're literally using this heating effect to create light.
But what if you're trying to send electricity hundreds of miles across the country through power lines? Well, then you want the exact opposite to happen, right? You don't want your power lines glowing white hot. That's just wasted energy. So for that job, we pick materials like copper and aluminum, specifically because their resistance is incredibly low. The goal here isn't to create heat, it's to get as much of that precious power to your house as possible with minimal loss along the way.
So that brings up a question. How do we actually measure the energy a device is using? Well, that's where electric power comes in. Power is just the rate at which a device uses energy. We calculate it by multiplying voltage times current, and the unit is the watt. So when you see a 100-watt light bulb, it literally just means it's a device that's burning through 100 joules of energy every single second it's on.
And it makes perfect sense, right? A 100-watt lamp is going to be a lot brighter than a 60-watt lamp. Why? Because it's consuming energy at a way higher rate. Since they're both plugged into the same wall outlet, they have the same voltage. That means the 100-watt bulb has to be pulling more current to produce all that extra light. And, of course, all that extra heat.
And just like that, we've come full circle. From that very first flick of the switch that closes the path to the final brilliant glow of the lamp, every single thing we've talked about is happening all at once. It's this beautiful, intricate dance between the push from the voltage, the actual flow of the current, and the friction of resistance. All of it perfectly choreographed by that one simple rule, Ohm's law.
You know, we've gotten really good at this. We've mastered materials like copper to move electricity and tungsten to make light. We've built our entire modern world on these principles. But it really makes you wonder, what's next? Is there some new material out there? Maybe a superconductor that works at room temperature? Or something we can't even imagine yet that could completely rewrite the rules? A material that could totally revolutionize how we power our world. Now that is something to think about.